Welcome back to Talk Tensors. You know, path loss is always a pain,
Tell me about it.
especially with everyone moving to these higher frequencies.
Yeah, absolutely, yeah.
Well, get this. Today, we're diving deep
All right.
into this paper that says they're tackling this head on.
Okay.
It's called path loss prediction, using machine learning with extended features.
Ooh.
And some researchers up at the Communications Research Center in Canada,
Okay.
they think they've cracked the code
All right.
to making path loss predictions way more accurate.
Wow, that's a bold claim.
It is, and we're going to break it all down
I'm excited.
for you today,
That's good.
with the help of our expert, of course.
Absolutely. And I think what's really interesting is that they've managed to do this by leveraging this pretty unique set of features
Okay.
that go way beyond just your typical distance and frequency.
Okay, now I'm really intrigued. But before we get into all the really technical stuff, can you kind of set the stage for us? Like, what is the traditional approach
Yeah.
to predicting path loss?
Sure. So for like decades,
Yeah.
path loss models, they were pretty simplistic,
Oh.
basically. They treated the environment as if it was this flat plane,
Okay.
ignoring stuff that we know is their like buildings and terrain.
Oh, okay.
And as you can probably imagine, that worked out, okay, for some really basic scenarios. But as soon as you get into
Yeah.
like a dense urban environment or anywhere with like complex topography, it just completely falls apart.
Yeah, it's like trying to navigate a city with a map from like the 1800s.
Totally.
You'd be so lost.
You'd be hopelessly lost.
Yeah.
So as you can imagine, as wireless networks have become more and more complex, researchers, they've tried to incorporate more detailed environmental factors into their models.
Yeah.
But often what happened was this just made the models super complex and really computationally expensive.
And that's where this whole idea of machine learning comes in, right?
Exactly.
It's like, okay, we have all this data, this complexity.
Yeah.
How can we use, the power of computers to,
Yeah.
find the signal and the noise?
Right. Yeah. But the real key here is like figuring out which of those data points are actually useful
Oh, okay.
for making the predictions.
Okay.
And that's where this whole idea of the extended features
Right.
in this paper come in.
Okay.
They use 6 specific features
Got it.
that when they're all used together,
Yeah.
really improve that prediction accuracy.
Okay, so let's break down these 6 features.
Okay.
The paper mentions frequency and link distance right at the top.
Right.
Those seem
Yeah.
pretty straightforward, right?
Yeah.
Like, obviously, different frequencies act differently.
Right.
And obviously, the further a signal has to travel, the weaker it's going to get.
Yeah. The weaker it gets. Yep.
So those are like the baseline, right? Like the foundation.
Okay.
But then they add these 4
Sure.
really, really interesting additional features.
Yep.
And they basically all quantify
Okay.
how much stuff
Stuff.
is in the way of the signal.
All right. I'm very intrigued. Tell me more.
Okay, so 2 of the features
Uh-huh.
focus on this idea of obstruction depth.
Obstruction depth.
So, like, how much is the signal actually blocked?
Okay.
And then the distance from that last obstruction
Okay.
to the receiver.
Gotcha.
So, imagine that a signal is trying to reach your phone.
Right.
These features are taking into account whether it has to go through like a ton of buildings
Okay.
or if it has like a clear line of sight
Okay.
for the last part of its journey.
So it's not just about like how
Yeah.
far it has to travel.
Uh-huh.
It's about what it encounters along the way.
Exactly. It's about the journey, not just the destination.
I like that. And then
Yeah.
they go even further
Okay.
and they get even more granular
Okay.
with features that describe like the obstruction density and distribution.
Okay.
So they look at how many contiguous blocks of obstructions there are.
Contiguous blocks.
Yeah.
Can you explain that?
Yeah. So think about it this way.
Right.
Like imagine you're looking down at the path that the signal is taking,
Okay.
like from above.
Got it.
A contiguous block is like a cluster of those obstructions
Okay.
with no gaps.
So like a solid wall of buildings?
Yeah, exactly. Like a solid wall.
Okay.
And they measure how many of those walls the signal has to go through.
Oh, okay. So like a signal traveling through a city with a few really tall skyscrapers would have a lower contiguous block count
Exactly.
than like a signal traveling through,
Yeah.
a dense suburb where everything is like 2 stories.
Exactly. Yeah,
you got it.
exactly.
Yeah. That makes
And
sense.
then the final feature
Yeah.
measures how evenly spaced out Those clusters are along the path.
Got it.
Essentially, it's like the standard deviation of their locations.
Interesting. Okay, so
Yeah.
a signal going through a city with evenly spaced skyscrapers would have like a high
Higher, yeah.
standard deviation.
Yeah.
Whereas a signal going through a city where all the tall buildings are like in one central business district
Right. Clustered together.
would have a lower.
Yeah, exactly.
Okay,
Yeah.
Okay.
So it's like they're mapping out the urban canyons
I'll take away, yeah.
that the signal has to go through.
Okay, so they're getting
They're getting really specific
really specific.
about how they characterize the environment.
Oh, right. And that's what
That's what makes this
unique.
unique. Yeah,
It's like they're giving the model X-ray vision.
totally.
You know, instead of just seeing a flat map,
Mm-hmm.
it can see
It can see all the nooks and crannies.
like all the little
Yeah.
in-betweens
Yeah,
that the signal has to go through.
exactly.
No wonder it's more accurate.
And you know what's really cool is that
Yeah.
they didn't even need some crazy complex neural network.
Really?
Yeah, they used a relatively simple, dense neural network with only 3 hidden layers.
Wow, I would guess,
Yeah.
way more complex
I know, right?
to handle all that stuff.
Yeah, but it really speaks to like the
Yeah.
power of feature selection.
So it's not just about like
Right.
throwing more data at it.
Yeah.
It's about,
It's about being smart.
yeah,
Yeah.
being smart and knowing what data to use.
Yeah, feeding it the right stuff.
Yeah, okay.
And that's really what sets this research apart from like previous attempts
Okay.
at using machine learning for path loss prediction.
Okay, I'm starting to see why you're so excited about this.
Yeah, it's pretty cool.
But I kind of want to zoom out for a second, okay? And like,
yeah.
where does all this come from?
Sure.
Like, you talked about the limitations
Yeah.
of traditional models,
Huh.
but like,
yeah.
where did those models even come from?
Right, like what's the history of this whole thing?
Yeah, like what's the history?
Well, history of path loss prediction.
Yeah.
Well, it all goes back to like the early days
Hmm.
of radio communication.
Right.
Scientists and engineers, they needed a way to figure out
Yeah.
how far radio signals could go.
Right. How far and like
Yeah.
how strong the signal would be
Oh, exactly. And how strong they'd be
at different distances.
at different distances. Yeah, because like
that's critical.
you can't build a communication system
Right.
if you don't even know
If you don't even know
if your signal is going to reach
if it's going to work.
the other end. Yeah.
Okay.
So those early models,
Yeah.
they were very basic.
Okay.
They were based on this idea that radio waves travel in straight lines
Okay.
and that,
Yeah.
the signal strength decreases proportionally
Oh.
to the square of the distance.
Oh, the inverse square law.
Exactly.
Yeah. I remember that.
From physics class.
From physics. Yeah.
Yeah.
Okay.
And those early models
Yeah.
worked, reasonasonably well for
Yeah.
like simple line of sight scenarios.
Wow.
Like you've got 2 antennas on
Right.
flat ground.
Right.
But as soon as you add in obstacles,
Right.
like buildings, trees,
Yeah.
even the curvature of the earth,
Right.
things get a lot more complicated.
A lot more complicated.
Yeah.
And I imagine as wireless communication
Yeah.
got more complex, the
Mhm.
models had to get more complex.
Absolutely. Yeah. So researchers started developing
Yeah.
more sophisticated models to try to account for
Right.
all that complexity.
Diffraction, right?
Exactly. Diffraction.
Or the signal bend.
Runs around obstacles.
Around obstacles. I mean,
Reflection.
reflection, yeah, where it bounces off
It
surfaces.
bounces off. Okay.
Yeah, yeah. And they started taking into account
Yeah.
the characteristics of the terrain, the type of vegetation,
Okay.
even like atmospheric conditions.
Right.
But
These more complex models,
yeah.
they were often very specific
Okay.
to particular environments or
Okay.
frequency bands,
Makes sense.
and they could be incredibly computationally intensive.
And as we move towards higher frequencies,
Actually,
like
yeah.
5G,
Yep.
6G,
hmm
like those models really started to hit their limits.
They hit a wall, yeah.
Yeah.
Because those higher frequencies, they're just way more sensitive
Right.
to obstacles and those little variations.
So we needed a new approach.
We needed a new approach, yeah, and that's where machine learning came in.
Right, and that's where this paper comes in.
Exactly.
Like the culmination of
It's like the culmination of all those years
all that.
of trial and error
Right.
finally leading to this breakthrough.
Yeah, and it's really cool because they're building on,
Yeah,
decades of research,
absolutely.
but they're pushing it forward
No, pushing it forward, yeah.
by bringing in machine learning
Exactly.
and by being really smart
And being smart about it.
about the data they use.
Yeah, exactly.
Okay, I'm really liking this.
It's really cool.
But before we keep going,
Yeah.
I want to understand, like,
Yeah.
how they did it.
Okay.
Like, what was their methodology?
All right. How did they actually train the model?
Right. Like, what data did they use?
So they took a really, really smart approach to data collection.
Okay.
They used a combination of public geographic information system data
Okay.
and then real-world path loss measurements
Oh, okay.
that they collected from drive tests.
So they're not just
like
theorizing.
Yeah, they're actually getting out there into the real world and seeing what's happening.
Grounding it
in reality.
in the real world. Okay.
So they used things like digital terrain models
Okay.
and surface models to create like detailed 3D representations of the environments they were studying.
Wow. So they like built a virtual replica
They basically built a virtual city.
of the city.
Yeah,
with all the
complete with all the obstacles.
buildings, the trees, the buildings, the trees, the terrain, everything.
That could affect the signal.
Everything.
Yeah.
Okay. And then
they went out and did
drive tests
to get real world data.
to actually measure what was happening.
Oh, okay.
So they
Combining the virtual.
They're combining the virtual and the real.
Bring this model.
Exactly.
Okay, and that allows it to.
They're able to train a model that can accurately predict path loss
To generalize.
in a bunch of different environments.
To new places.
To new places, even places it's never seen before.
That's really cool.
Yeah, that's really powerful.
Okay.
Because if you want to use this to design and optimize
Real world networks.
real world networks, it can't just be specific.
It has to be able to generalize to one tiny little area.
Okay. This is
really cool.
really cool.
Yeah.
Well, we've been talking a lot about
Mm-hmm.
like the technical stuff.
Yeah.
What about
nitty gritty details?
Yeah, what about the bigger picture?
Right. Like, what does this actually mean?
Yeah, like how could this change
Yeah.
the way that we design and operate wireless networks?
So for starters, imagine being able to predict path loss with this much accuracy that you could actually optimize where you put base stations to provide seamless coverage.
So no more dead zones.
Even in like the most difficult environment.
No more dropped calls.
More dropped calls, yeah.
That would be amazing.
That'd be amazing.
Yeah.
And we could even use these predictions to dynamically adjust network parameters.
In real time?
In real time.
Wow.
Responding to changes in like user demand or environmental conditions.
So like a network that's
a truly intelligent network.
Really
a truly intelligent
and adaptive
and adaptable network.
And what's going on?
That's constantly optimizing itself for like peak performance.
Wow.
And the implications.
Yeah.
They go way beyond just like improving our cell service.
Yeah.
Think about like
the Internet of Things.
The Internet of Things, right.
All those billions of devices.
Billions of devices all connected wirelessly.
Yeah.
Accurate path loss prediction.
Yeah.
That could be critical.
For making sure
that all those devices can talk to each other.
That they can talk to each other reliably.
Reliably and efficiently, yeah.
And efficiently, and that's
especially for smart cities.
Smart cities.
We're relying on these networks, all these sensors and networks.
To manage things like traffic.
To manage everything, yeah.
Energy.
Traffic energy.
Everything.
Right,
and you can't forget.
And autonomous vehicles. That need constant,
reliable communication.
Reliable communication to be able to navigate safely.
To work at all.
Yeah.
Wow. This research really could
It's pretty crazy.
affect like every
when you think about it.
Aspect of our lives.
How far-reaching it is.
Yeah.
It's kind of amazing.
It is.
To think that it all stems from something as seemingly technical as path loss prediction.
It just shows them.
It just goes to show
the fundamentals.
That even like the most fundamental aspects of wireless communication
can have these huge implications.
Can have these huge impacts
on how we
live and work.
Live, work, play.
And interact with the world.
Yeah.
Yeah.
Okay. Now, my mind is racing with possibilities.
Good.
What if we took this research even further?
Turn further, yeah.
What kind of
novel notions does this spark for you?
Are we thinking about?
What are we thinking about? Yeah, so what I think is really fascinating here is that this paper is focused on predicting path loss in static environments.
Right.
What if we could create a system, a real-time path loss prediction system that's constantly
Adapting to changes in the environment.
Yeah, like imagine a network that can actually anticipate
Oh, wow.
changes in signal propagation.
Okay.
Because of things like, rush hour traffic,
Okay.
sudden downpour,
Oh.
even a flock of birds.
Wow. Okay, so we're picturing a network that's like
It's almost like a living organism.
a living organism
Yeah.
that's constantly sensing and responding.
Yeah, constantly sensing and responding
To everything that's going on.
to its surroundings. Yeah,
But how would we even
that's a great question.
begin to build something like
It
that?
would be a huge undertaking,
Yeah.
but
Yeah.
we would need
Okay.
a ton of data.
Like a ridiculous amount of data?
A ridiculous amount of real-time data from a ton of different sources.
Okay.
Think about like sensors on drones,
Okay.
weather stations,
Okay.
traffic cameras,
Uh-huh.
even like smartphones themselves.
So we're talking about a network that's not just
That's not just transmitting data.
transmitting data, it's also
gathering
data about
gathering data about its environment.
its environment
Yeah.
to make itself better.
To make itself better. Yeah.
Wow.
To constantly refine its performance.
And-
And we would need,
We would need some pretty
really
algorithms
sophisticated algorithm.
to process all that
Yeah.
on the fly.
That could,
Wow.
make predictions in real time.
That sounds like a huge
It would be a huge
computational challenge.
computational challenge.
And
It
yeah.
certainly would be. But
Yeah.
with all the advancements
Mhm.
in things like edge computing and distributed intelligence,
Okay.
it's
What's becoming possible?
it's becoming more and more possible.
Okay.
We could have like localized processing units
Right.
that are handling data from their
Right.
immediate surroundings
Right.
and then sharing
Sharing their insight.
their insights with the larger network.
So like a decentralized
A
system
decentralized system, yeah.
where each part is
Where each part is
contributing to
the whole
thing.
to the overall intelligence, yeah.
Almost like an ant colony, right?
That's a great analogy.
Where each individual ant,
Yeah.
makes decisions based on
Based on,
their local environment. Yeah.
but collectively,
They create
this
sort of super intelligent.
really efficient and adaptable system.
Yeah.
Yeah. And it highlights the power of
Yeah.
collective intelligence, which is something machine learning is really good at
Tapping into.
tapping into. Yeah.
I'm also thinking about the potential
Okay.
to use this to save energy.
Oh, absolutely.
Right. Like
Okay.
if we can
If we can anticipate those changes
anticipate the
in
change
signal strength,
in signal strength.
we can adjust how much power
Right.
the base stations are using.
We don't have to blast them at
Exactly.
full power all the time
We can avoid
Wow.
blasting out those high power signals
when they're not needed.
when they're not needed, which saves energy
Saves energy and reduces
and reduces interference. Yeah.
Okay.
But
So
that could be really helpful,
yeah.
especially for like mobile devices.
Right. Because our phones are
For
always
just
trying to
less. Save battery.
save battery. Yeah.
Yeah.
Like a win-win.
It's a win-win.
A more efficient network and longer lasting devices.
I'm really starting to see how this
Yeah.
seemingly, technical paper.
How something that seems so
Yeah.
technical can have about path loss could have
big impact.
such a big impact. Yeah.
Yeah.
It's not just about
It's not just about
It's-
making the network work better.
making the network
It's
better.
like about making an
Creating a more
sustainable, intelligent,
connected world.
connected world. Wow.
Yeah.
Okay, that is a really
It's pretty cool.
cool thought.
Yeah.
Let's take a quick break
That's good.
and we'll come back and talk about
Go
some
ahead.
more of the implications of this research.
Looking forward to it.
Yeah.
It really highlights like this shift we're seeing in wireless communication research.
Oh, interesting.
It's not just about like physics and engineering anymore.
It's like we need to bring in all these other tools
Yeah.
and ideas from other fields,
Totally. Yeah.
like machine learning, data science,
yeah.
to solve these problems.
To tackle these like really complex challenges.
Yeah, yeah.
It's becoming,
It's a much more interdisciplinary field. A truly interdisciplinary field, yeah.
which is really exciting.
It is, yeah.
But let's get back to those novel notions
The notions are
that you mentioned. You're
Yeah.
talking about this real-time path loss prediction system
right, yeah.
that adapts to the changing environment.
That's constantly adapting.
Yeah.
Yeah, imagine like a network that can actually anticipate
Click.
changes in signal propagation
Okay.
due to things like rush
Oh.
hour traffic,
Okay.
a sudden downpour,
Right. Right.
even like a flock of birds flying overhead.
Okay. I'm picturing like
Yeah.
a network that's almost
It's almost like
like a living, breathing thing.
a living organism.
Yeah. that's like sensing everything around it
Constantly sensing
and responding.
and responding to its surroundings.
But how would we even...
That's the million-dollar question.
Yeah, like how would we even begin
Yeah.
to build something like that?
So it would be a massive undertaking.
Okay, but I think we need a few key things.
Okay.
First of all,
Yeah.
we'd need a ton of data.
A ton.
Like a ridiculous amount.
Like an insane amount of data.
Of real-time data.
Real time.
From all sorts of different sources.
Okay. Okay.
So think about like
Okay.
sensors on drones,
Okay.
weather stations,
Yeah.
traffic cameras,
Makes sense.
even smartphones.
So we're talking about a network that's
a network that's not just
not just transmitting data,
transmitting data,
but it's also
gathering data
gathering data about
about its environment.
its environment.
To constantly refine its performance. Adapt.
And we need
And then we need
some pretty intense,
some very sophisticated
algorithms
to be able to process all that data and make predictions
on the fly
in real time.
in real time. That sounds like a
That's a huge.
computational challenge.
Yeah.
It would be.
Yeah.
But with all the advances in things like edge computing, distributed intelligence, it's becoming more and more feasible.
More and more feasible.
So we could potentially have like
Yeah.
localized processing units
Okay.
that are handling data from their little immediate surroundings and then sharing those insights.
Sharing their insights.
With the larger network.
So like a decentralized system.
A decentralized system, yeah.
Where each part
is
contributing to
the whole overall intelligence.
Almost like an ant colony.
That's a perfect analogy.
Where each individual ant is making its own decisions.
Based on its local environment.
But then as a whole,
but collectively,
the colony is super intelligent.
Super efficient and adaptable system.
And adaptable.
Yeah.
That's really cool.
It is. And it really highlights like, the power of collective intelligence.
Yeah.
Which is something machine learning is really good at tapping into.
I'm also thinking about the energy savings.
Oh, absolutely.
That we could get.
Huge potential there.
If we can anticipate
those changes.
The changes in signal strength. We can adjust.
The power.
Power output. We don't have to just...
Exactly. We don't have to blast out.
At full power.
High power signals when they're not needed.
All the time.
Yeah.
So that would save energy. Reduce interference. And that would be especially good.
Especially for our
mobile devices.
Yeah, because our phones are always trying to save battery.
Always trying to save battery life. So it's a win-win.
It's a win-win.
More efficient network, longer lasting devices.
Okay, I'm really seeing how this seemingly, it's amazing how something...
Technical paper.
This seems so technical.
Can have
that floss.
Such a huge impact.
Could have these huge implications for like everything.
Yeah.
It's not just about
like improving network performance.
The network working better.
It's about creating
improving a better,
more sustainable
and
intelligent, connected world.
Wow. That's a really powerful thought.
Yeah. It's pretty cool when you think about it.
Okay. I love these novel notions.
Novel notions, yeah.
But I kind of want to bring it back down to earth for a minute.
Okay. Back to reality.
Yeah, and talk about some of the limitations.
Okay, the limitations.
And every
it's important to acknowledge that even like the most groundbreaking research has limitations.
So what are some of the limitations?
Some of the challenges
that researchers still need to address.
Okay.
So one of the biggest challenges is data availability. You know, we've talked about how these models rely on having access to good data. Detailed, accurate information about the environment.
Which isn't always easy to get.
Especially in like cities that are constantly changing. So we need like better, more efficient ways
to gather this data.
Whether
that's through aerial surveys.
Okay.
Mobile sensing.
Yeah.
Even crowdsourcing.
So like using our phones.
Potentially, yeah.
But that brings up a whole other
issue
of privacy.
A whole other set of challenges around privacy.
Yeah, because if we're using our phones to collect data.
Privacy is like paramount.
You have to be really careful about that.
We need to make sure.
That any data collection is done with full transparency.
Right.
And user consent.
And users know
Yeah.
what's going on.
Exactly.
I'm also thinking about
Yeah.
just the computational complexity
Oh, yeah, for sure.
of these models.
This is a big challenge.
Even with
a relatively simple neural network,
yeah,
processing all that data
if it's
in real time is a lot.
Ask.
But
And as we add in more features and the models get more complex, those demands are just going to increase.
So we need to get better at.
We need to develop more efficient algorithms.
Better algorithms, better hardware.
And hardware architectures to handle all that stuff.
Yeah.
And, I think another challenge is interpretability.
Interpretability.
Yeah. Like right now,
a
lot of these models are kind of like black boxes.
Black boxes? What do you mean?
They make good predictions.
Okay.
But we don't always know why.
Like we don't really understand what's going on inside.
So they're getting the right answer.
Yeah, they're getting the right answer.
But we don't know how.
They're
doing it.
Yeah.
Which is a problem.
Which could be a problem.
If we want to.
Especially if we want to trust them. To make
important decisions.
About our networks.
About, network design and operation.
Right. We need to know.
We need to be able to understand
how they're coming up.
How they're getting to those conclusions.
With those answers.
Yeah.
Okay, so it sounds like...
So there's a lot of work to be done.
A lot of work to be done.
In terms of making these models more transparent.
More transparent, more...
And explainable.
Yeah.
It sounds like we've got our work cut out for us.
Yeah, it sounds like there's no shortage of challenges.
No shortage of challenges.
To keep researchers busy.
But you know what?
For a long time.
Those challenges also represent opportunities.
They also represent opportunities to really push the boundaries of this field even further.
And it's not just about the technical stuff.
It's not just about the technical stuff.
It's also about
the societal implications.
Societal implications, yeah.
Right. As these networks
become
more powerful
and more pervasive.
Yeah.
We need to be having conversations about...
You need to have those hard discussions.
Yeah, about how they're being used. Who has access to them. And how we can make sure...
And making sure that
they benefit everyone.
Beneficial to everyone.
Yeah.
Not just a
select few.
A select few, right?
Exactly. Technology is a tool.
It's a tool.
And it can be used for good or for bad.
Right.
It's up to us.
Right. It's up to us.
To shape its development and deployment. To shape it.
In a way that aligns with our values.
To make sure it's used ethically.
Absolutely.
That is a really important point.
It's an important conversation to be having.
Yeah, this has been a really thought-provoking discussion. And I feel like...
It feels like we've only just scratched the surface.
We've only just scratched the surface.
Of this, really complex...
this really complex topic.
And a fascinating topic.
Yeah, and I think...
A Novel Notions segment.
Novel Notions are a great way to...
Is the perfect way to wrap up this deep dive. So let's unleash our imaginations.
Okay, I'm ready. Let's do it.
And see what other crazy ideas.
Hit me with your...
This paper has inspired...
Most outlandish notion.
Okay, so we've been talking about using sensors to gather data about the environment.
Right.
What if we could go beyond just sensing and actually start manipulating the environment?
Whoa.
To optimize signal propagation.
Hold on. Manipulate the environment.
Imagine a city.
What do you mean?
Where buildings are coated with a special material that can dynamically adjust its electromagnetic properties.
Okay, I'm picturing a camouflage suit.
Yeah.
That can blend in.
Almost like a chameleon.
With the surroundings.
Yeah.
But for buildings.
Okay. Now imagine that this material could be controlled in real time to redirect signals, create virtual antennas, or even block interference.
So we're talking about turning the entire city.
We're talking about turning the city
into
to a giant
antenna.
Programmable antenna array.
Wow.
Yeah. It's pretty wild.
Mind-blowing.
But we could
but also incredibly complex.
Dynamically shape.
Right.
The wireless landscape.
And probably really expensive.
To optimize coverage.
Yeah.
Minimize interference.
Okay.
We could even create personalized communication zones.
That would be...
I know, right?
incredible.
A pretty crazy idea.
It's a crazy idea, but it would also...
But it would be a monumental undertaking.
Yeah.
It would raise a lot of
Like ethical questions.
ethical and logistical questions.
Yeah, like who gets to control that?
Yeah.
Like who gets to decide
to control
who gets the good signal
these programmable environments.
and who gets the bad signal?
Yeah. And how do we make sure
How do we make sure
that everybody
it's
has
equitable
access
Yeah.
to the network?
Those are
big questions.
huge questions.
And it's important to have these conversations now,
Oh, yeah.
while these technologies are still
Before it's too late,
in their early stages of development,
right?
because once these systems are in place,
Yeah,
it might be very difficult to change them.
right. Because technology is powerful,
Technology is incredibly powerful,
but it's not
but it's not a magic bullet.
a magic solution to everything,
Yeah.
right?
It's up to us
We have to
to make sure that it's used responsibly
guide it.
and ethically.
Yeah.
That's our responsibility.
You've given us a lot to think about.
A lot to think about, yeah.
This idea of
This programmable wireless environment.
programmable wireless environment.
It's pretty wild.
It's pretty wild.
It's both fascinating
Yes.
and a little bit unsettling.
Yeah, a little bit unsettling.
But I think it's a good reminder
Yeah.
that the future of technology
Yeah.
is full of possibility,
Full of
both
possibility.
positive and negative.
Yeah.
And it's our responsibility
Our responsibility
to steer it in the right direction.
to steer in the right direction
Yeah.
to make sure it benefits humanity.
Exactly.
Okay. This has been an incredible
It has been a fascinating
deep dive.
dive into
Value.
path loss prediction
Path loss prediction.
and its implications
Yeah.
for the future.
I can't wait to see
Me too.
what comes next.
It's a rapidly evolving area of research. I
Yeah.
have no doubt we'll see even more
Yeah.
groundbreaking advancements
I'm sure we will.
in the years to come.
Yeah, it really is like we're on the cusp of something completely new,
It is. It's pretty mind-blowing.
where the environment itself is part of the network.
Yeah, the line between the physical and the digital is getting
It's blurring.
really blurry. Yeah.
But okay, let's bring it back down to
Okay,
this
okay.
paper.
Okay, it's the paper.
Because even though all those future possibilities are like
Yeah,
super exciting,
they're definitely exciting.
this research is already
This research is already
a big deal.
a significant step forward
Yeah.
in path loss prediction.
They've shown that we can get much more accurate
Yeah,
predictions
way more accurate
than those old models
than traditional models.
by using machine learning
Absolutely.
and choosing those features carefully.
It's all about the features.
Okay, so speaking of today,
Yeah.
I'm curious,
Okay.
like, what kind of tools are out there
Sure.
for people who want to,
Yeah.
play around with machine learning
Okay.
for path loss?
So, like, what's available?
Yeah, like what's available? Is this something that requires like,
Yeah.
tons of specialized software?
Well,
Or,
not necessarily. There are a bunch of open source machine learning libraries and platforms
okay.
like TensorFlow and PyTorch
Okay.
that make it actually pretty easy
Oh,
to
okay.
get started.
So even someone without like
Yeah.
PhD in machine learning
Even somebody with, a basic understanding of
can
like,
experiment with this.
totally experiment with these techniques.
That's cool.
Yeah, there are tons of like online tutorials and resources
So there's really no excuse
that can walk you through the process step by step.
to not at least try it out.
Exactly. Yeah. So there's really
That's really cool.
no excuse not to dive in and give it a shot.
I'm also thinking about like
Yeah.
the potential for collaboration.
Oh, absolutely.
Imagine
Yeah.
a bunch of researchers, developers
Yeah.
sharing their data,
Sharing their data, their model.
their models. Like we could really
You could accelerate progress.
progress in this field
Yeah.
dramatically.
Imagine a platform.
Yeah, imagine like a platform
Where
where
people
people
could contribute their,
yeah,
local path loss measurements.
share their model,
Share their models. Yeah.
work
Or
together
work together to create.
like
It's super accurate.
a robust prediction
Total
tools.
path loss prediction.
It'd be like this global path loss prediction network
That's constantly learning.
that's constantly learning and evolving
Wow. That's
as
a
more data gets fed into it.
novel notion in itself.
That's a pretty cool idea.
That's really cool. It really highlights,
Yeah.
the power of community-driven research.
Well, I think on that note
Yeah.
of
The
collaboration
collaboration.
and, amazing possibilities,
Boundless possibilities.
it's time to wrap up.
I think it's time to wrap up this deep dive.
Let's deep dive.
It has been a truly fascinating exploration
of path loss
of path loss prediction
from, the basic principle
from the fundamentals
to the cutting edge research.
to the cutting edge.
That's really pushing the boundaries of what's possible.
We've covered a lot
We covered a lot of ground
today from, where it all started.
The history of,
But where it's going.
path loss modeling
Yeah.
to the exciting potential
To those crazy novel notions.
of machine learning.
Yeah.
Of course,
Yeah.
all the mind-blowing novel notions.
If you want to learn more
If you want to learn more about this
topic,
be sure to check out the full paper.
check out the paper. The link is down in the show notes.
Link in the show notes.
And as always,
we
encourage you to share your thoughts
let us know what you think.
and your own novel notions
Your novel notions
with us on social media.
on social media.
We love hearing from you
Yeah, we love hearing from our listeners.
on engaging in these discussions
Engaging with you all
about the latest and greatest
about all this cool new stuff.
in machine learning
Yeah, thanks for joining us
and beyond. Thanks for joining us
on this deep dive
on this deep dive into
into the world
the world of wireless communication. Until next time,
Until next time,
keep those neural networks firing.
keep those neurons firing.